Hey, Year 11! Thanks for coming, guys. This is the last webinar of the year for you guys. I'll try and be as quick as I possibly can this evening. I'm going to be doing two things today. I'm going to be doing a run-through of the specimen paper 2, and I'm going to be giving you guys some predictions for your paper that you're going to have in a couple of weeks. Okay, so I'm going to get straight into it. Usual, share screen, and then let's have a look at our notes. Okay, right, so now it's really nice to be able, hey Donna, thanks for coming. Oh, I've got my usual followers, love that you guys are here. Okay, so I guess I'm just going to quickly write onto here that the main focuses for today, my learning objectives are a run-through of paper, run-through of specimen paper, spec paper 2, and I'm going to give you some predictions. So predictions, hopefully, that are going to really help you out for your exam in a couple of weeks. So it'll give you a bit of an idea of what to focus on and hopefully be of some use. Okay, so now paper 1 that you guys sat a few weeks back was a relatively easy paper. So I'm expecting them to rank up the difficulty a little bit on your paper 2. So definitely worthwhile going through this specimen and then having a look and seeing how difficult they can make it. Okay, so question number 1 drops us back into our same good old-fashioned particle theory, but this time, of course, they're focusing on observations. A few drops of liquid bromine are placed in the bottom of a gas jar. A few crystals of solid iodine are placed in the bottom of a gas jar. The open ends of the gas jar are covered with a lid, and the gas jars are left for several hours under the same conditions. The diagrams show that the gas jars, just after the bromine and iodine are added, and after several hours. So really nice to be able to look at the difference, because we know that bromine, of course, is going in as Br2, but as a liquid, and that's important. And then what it's doing is it's evaporating off the surface, evaporating off the surface, and then is filling the jar, and you can see it's spreading out. Notice that it's darker. This one here, the after several hours, in terms of compared to the iodine, that the darkness seems to have gone further with the bromine than it has with the iodine. Okay, and the iodine is not evaporating. The iodine is subliming. So it's really nice just to have that sublimation and evaporation discussion and the difference between them. Iodine, of course, is going in as I2, as a solid, and turning into vapor, skipping the liquid phase. So it then says, state the color of the bromine vapor and the iodine vapor. So the bromine vapor, of course, is brown. And bromine is a lovely element because, of course, the colors are nice and easy to remember. It's the first 2 letters of the word. Bromine is brown as a liquid. It's a brown liquid. It is a brown gas. And in solution, it is orange. Now, iodine, it's quite nice actually to see some actual pictures of this as well, because I do like seeing these. So if I quickly do a quick search for bromine and do images, we can clearly see that we've got a brown liquid with a very dark brown gas for bromine. But then, of course, when you have it in solution, if you have bromine in solution, you tend to see it as orange. There's bromine as a solution. We get this orange color. And then if we do iodine, so if I quickly switch this, we've got a grayish black solid, a gray solid with purple vapor. So there's our gray solid. And you can actually see a very slight purpley haze around that. But of course, we know that iodine, of course, is subliming. So it's far more slow in terms of its process. And then we get this purple vapor. And when iodine, of course, is in solution, it's brown. So iodine is one that I'm very much having a prediction of it to make an appearance. It's got these 3 observations, which are all very distinct from each other. So I would definitely make the effort to learn all your halogen colors and particularly remembering your iodine. Okay, so iodine is a vapor being purple. Just to add one more thing, which is iodine in water is brown, but iodine in an organic solvent like hexane is purple. There is a 4th observation with iodine. if you want to actually come and ask me in school and actually see that, I'm quite happy to show you it. The diagram shows that the molecules of bromine and iodine have spread out in the gas jar, name the process. We like this diffusion, nice and straightforward. I'm very much thinking that they're looking to make this harder, so they'd probably want you to describe in terms of particle theory the process of diffusion, and moving from, and of course for bromine, it would be the liquid evaporates, turning into a gas, and then moves from an area of high concentration to low concentration because the particles are moving around in the gas randomly. Okay, next. So a nice simple equation. So it says that the chemical equation for this change for bromine is Br2 liquid going to Br2 gas. This change involving iodine is called sublimation. Write the equation for it. So that's nice because what they're testing you on here is your state symbols and recognizing that we're skipping a phase for iodine and going straight over to a gas. So quite nice because they're making you write an equation, which is actually relatively unusual. If you were doing a dissolving equation, then you'd be putting in bromine liquid, and then it would be forming bromine aqueous. Okay, on to the next question. So the next one drops us into electrolysis straight away. And electrolysis did not appear on paper one, of course. It is purely on the higher level specification. It is going to make an appearance. Make sure you have done your revision. Now, in the specimen paper, they've given you lead bromide. So I'm expecting them to give you a brine solution. So sodium chloride aqueous, definitely worthwhile doing a little bit of revision of that, and also having a look at your other salts that you've done in the course of iGCSE. And it says, when the apparatus is set up and shown, electrolysis does not occur. State what must be done for electrolysis to occur. Now, the reason why it doesn't is because we know that for electrolysis, you've got your electrodes. Let's highlight our electrodes. We've got our two electrodes, and of course, we need to put the electricity through an electrolyte. And an electrolyte, of course, is a liquid or solution that can conduct electricity. Now, in this case, you'll notice this key word, solid lead bromide. Now, it is ionic, but remember, ionic substances do not conduct. So lead bromide, PbBr2, as a solid will not conduct because the ions are locked in position and are unable to move through the structure. However, we know that lead bromide will conduct when molten, aka liquid. So we're going to have to heat this until it melts, and then it will conduct because the ions are free to flow, free to move, and flow through the structure. Flow through structure, carrying charge. I'm just going to put struck, carrying charge. Cool. So, and remember, it is carrying charge. It is the ions that are carrying the charge in this particular case. So it says, state what must be done to the electrolyte, heat until the lead bromide is a liquid. So we're just freeing up those ions to be able to move. So liquid. You could, of course, also add water, but then you're going to change your products of your electrolysis. Make sure you do a little bit of revision. Electrolysis needs to have a bit of focus for your revision, folks. Okay, when the necessary change is made, electrolysis occurs. Particles A, B, and C move in the directions shown by the arrows. I identify each of the particles A, B, and C. So we know that we've got electrical cables here, and electrical cables, of course, are made of metal. And the charge carriers in that case are the electrons. This is the sea of delocalized electrons that are flowing through the structure. So we've got electrons as A. Right, the next one is we've got to be a bit more careful with this because we've now got, I'm just suddenly realizing I need to, yeah, okay. We've now got the cathode. So the cathode, now of course, and cathode and anode, people often say, I forget what their charge is. So we remember panic, which is positive anode, negative cathode. Right. So if that's negative, what's B going to be? And the answer is B must therefore be a positive ion. So in this case, I'm just going to shrink my pen down. B is going to be lead 2+, heading towards the negative cathode. Next, what must C be? C needs to be a negative ion. And who's the negative ion in this particular case? And that's bromide. So Br minus. So nice to see that what they're testing you on is your ability to recognize your charge carriers and be able to identify those people from a given substance name and being able to then name them. Cool. So I put electrons for A, lead 2+ cation for B, and C is a bromide. Please notice it is not bromine. It is a bromide anion. Cool. And I've also given the formula, just to be absolutely sure. Cool. Next. Nice question to start off with. Okay, write the ionic equation for what is occurring at the cathode. So we are expecting these, folks, and in my previous webinar on ionic compounds and electrolysis, I showed you that you only have 7 electrolysis equations to learn. So, and here was one of them. So lead 2+ is going to gain 2 electrons, and you're forming Pb solid. Let's add some state symbols here. So the Pb2+ ion is actually going to be a liquid, of course, because it's flowing around. And I'm going to form lead solid. So I'm actually going to form lead metal will appear on the cathode, and it will turn to a silver shiny metal on the surface. It is gaining 2 electrons. Now, I just want to give you a second example of these equations. If we weren't doing lead 2+, let's say we were doing aluminium 3+. Now, aluminium 3+, once again, will gain electrons, and it will form aluminium metal. But the question is, of course, how many electrons am I going to gain? And of course, the answer comes from my charge. So I'm going to need 3 electrons to cancel out that +3 charge. And so just be aware that the charge on the cation is going to decide how many electrons you're going to add. State what type of a reaction is happening at the cathode, and it's actually described as a reduction. Explain why for 1 mark. Reduction is the gain of electrons, 1 mark. And I know it's only 1 mark here, but I do want to give that extra detail because I don't know if they want it. So now I'm going to say, and lead 2+ is gaining 2 electrons. Therefore, it is going through reduction. Cool. So nice to make that clearer with the second bullet point and actually linking it back to my equation that I'm using. Okay, next question. Okay. Oh, do you know what? I loved seeing this because Year 11, I've loved doing all of my various demonstrations for you. And bottle rockets is one of my favorites. So methane reacts with oxygen in an exothermic reaction. If a burning spill is placed near a mixture of methane and oxygen, there is an explosion. A teacher fills a plastic bottle with a mixture of methane and oxygen. He places the bottle on the sloped ramp, and then he puts the burning splint near the end of the bottle. An explosion causes the bottle to move up the ramp and shoot off the end. The teacher measures the distance the bottle travels. Seems very reasonable. The volume of the bottle is, that's interesting. They've given us a sudden piece of data. We're going to need that. So it then says the table of his results are below. So we've got volume of methane used is 0, volume of oxygen 1,000. And then they slowly switch over. And we've got this distance traveled by bottle in meters. So the first thing is they wanted you to fill in the numbers, and I think most people would have been able to have done this, recognizing that you've always got to keep the total volume the same. And that, of course, would be one of our control variables. The other one would be other examples. Would anybody here like to offer me a suggestion looking at the diagram of a control variable for this particular reaction? I'll give you 10 seconds to apply. Control variables. Oh. Control variables. Keep the ramp the same. Connor, I need more detail. That's better. Yo's filled in your answer. Yeah, slope of the ramp. So, by the way, it's interesting that you'd put the slope. I don't think they'd like you. You'd definitely get the mark, Yo. And I know, Connor, I know that you meant the slope. What I would probably want to actually clarify here is the angle of the slope. We definitely want to keep that the same. Because the problem is, if you say the slope, I reckon EdXL in their infinite wisdom would actually say ignore slope, because the reason being is that technically the ramp is technically a slope, but in order for you to define it, you need to be saying the angle of which the slope is placed at. So Obviously, remember that particular thing, looking for those detail answers. Is there any other ones that we'd want to do? Maybe the length of the ramp. Would that matter? Potentially. If it was shorter, it's going to begin its descent quicker. So definitely the length of the ramp. And also the bottle as well. Because if I change the bottle, I might change the opening on the bottle and it would be wider, which would then, of course, change the distance traveled. So a few variables there. Okay, they ask you to plot the graph, and they're very clear on this. They say draw the lines of best fit for the first 3 points and then draw a line of best fit for the last 3 points. So you can see how I've done it. I've put on my numbers. Here are my first 3, and then here are my second 3. And then I draw my lines of best fit and see where they intersect. And of course, that's going to come up later. Use the graph to determine the volume of methane needed to produce the greatest distance traveled by the bottle. And you just use your same thing as normal, folks. Use your clear 30-centimeter ruler. Draw your dotted line down. You must show that. Draw it on your paper. That is important. And read off your answers, and you'll be absolutely fine. Nice and easy. Graphs are always good points. Suggest why the teacher should obtain more results between 200 and 600 centimeters cubed of methane. Right, that's interesting. 200. I want to look at 200 and 600. Right, so hang on a minute. If we go from the 200 to the 600, we just haven't bothered to do any more readings between those two. And in order for us to, because I think it would be fair to say, we've extrapolated, that's what this is called, we have extrapolated these lines by quite a long way. And that's how far we've extrapolated. For us to get a better answer than 320, all we need to do is more experiments within that region. So the more results would mean a better line of best fit and more accurate point to where they cross. Remember that whenever you repeat or do more experiments, you're going to get a better line of best fit. Just to quickly explain that, because whenever you do an experiment, students often say, how many points do I need? How many experiments do I need to do? 3 is never enough. The reason being is if you have 3 points, that there must be a curve. Hey, Nikita, thanks for coming. So these 3 points would lead to a curve, but it might not be. Any one of the points could be an anomaly. So when I do the 4th point, I immediately start to realize that I have an anomaly within my data. But I still don't have enough because I still want to know whether or not that line is true. So I add a 5th. And at that point, it makes my line far more reliable. So if I want to improve that, if I do half a dozen extra experiments, I'm going to get a much more reliable line of best fit. I'm having to do less guesswork within it. So you do more, if you repeat, students often don't realize why you're repeating an experiment. You repeat an experiment in order to identify anomalies, discard them, and calculate a better average. Why would you do more experiments within the range of different numbers? So that's this question. It'll give you a more reliable and a better line of best fit. Once again, being able to spot anomalies and discard them. So that question is definitely one to pay attention to. I haven't seen an awful lot about the repeating, and it's quite nice just to mention those and make some notes on them. Why do we repeat? In order to be able to spot anomalies, discard them, and calculate a better average. So, for example, on the repeat repeat question, if I had data and I had done an experiment 3 times and I got 23, 22, and 45. Well, at that point, we know the 45 is an anomaly because these two clearly are very similar, and that is nowhere near the same value. Well, how do you know that the 45 isn't actually the wrong answer? Well, if you do a 4th and you get 22, then you're absolutely crystal clear that you're going to discard this, add these 3 together, and you're going to divide the whole thing by 3 and get a better average. You repeat to be able to spot anomalies that don't fit the trend, discard them, and calculate a better average. Now, just to mention your data question, I think you're definitely going to have, making predictions here, folks, you are going to get given chemistry data. So just to quickly show you, so if I do GCSE chemistry data, and I go question, and I go enter, what I'm going to get, we're going to get these little tables of data that we're going to see at GCSE. Let's see if I can spot one. Come on, be nice, Google. Be nice to me. Let's have a look at, let's have a look at this one. So if we look at our data, you're going to get this data table. And the important thing, what you're doing with it is looking for repeats. That's not a good repeat one, actually. Let's do GCSE chemistry rates of reaction data question. I'm pretty sure that'll probably give me what I want. Yes. So I think the first one probably might work there. I quite like time taken for the cross to disappear. There we go. So you're going to get given a very simple set of data. And what you need to realize is, guys, they're going to have an anomaly somewhere. And you should always just keep your eye out for them. It's really nice, actually, to see that data, because all that data is very consistent. I can't see any anomalies in that. In the first string, all very similar. In the second one, very similar. 130, 128, 128, very similar. 95, 93, 94, very similar. There's no errors in this data. They're all very, very close. So that one, there's no real errors in the data. There's no anomalies. But they're going to give you one, and they're going to ask you to calculate an average. Guys, please remember, if you see an anomaly, ignore it, cross it out, and don't include it in your average. Really important. I can't find another set of data, so I'll leave it at that point. Okay, let's go back to here. Okay, next. This question is about ethanoic acid. So you guys know that you have had no organic up to this point, and there's alcohols, carboxylic acids, and esters on this paper. This question is about what is the structural, that's the key thing, structural formula for ethanoic acid. Now remember, folks, I've done this in my organic webinar. We have got molecular formulae. There's ethanoic acid's molecular, tells me nothing. We have structural formulae. I've made an error. There we go. Structural formulae. That now shows you a written formulae that shows you the way that the atoms are arranged. We then have displayed. Please remember to practice your displayed. Do not, the internet is a great resource, but that bond must not disappear, year 11. Please don't make that vanish. So there's your displayed. I'm tempted to do empirical as well. Look at that. We can do the empirical. CH2O, that tells me absolutely nothing. Is there any others I particularly want to do? No, that's all I want to do at GCSE. So here's your structural. That's structural. And of course, the other one, of course, that you're going to be asked for is displayed. So this is our displayed formula. Cool. Next, so quickly looking through it. First one is an alcohol. Definitely not. Second one is an ester. It's a kook. It's always nice that. Kook tells you that it's going to be an ester. Next one is a koo. God, I lost my voice there. A koo is a carboxylic acid. There's my answer. And the last one is thrown in just for fun. That is something you do not know, year 11. It's called an ether, a long lost forgotten family. But they're throwing it in there because they're going to hopefully get you to try and trick people into thinking that that's the right answer, but it definitely isn't. Next, an aqueous solution of ethanoic acid is weakly acidic. What is the possible value for the pH of a weak acid? So guys, this is a lovely question because I actually teach when you do weak acids. So we've got a strong acid. Let's quickly jump back onto the internet because of course what they're testing you on here, folks, is your year 7 memory from acids and alkalis. Because if I go pH scale and I click OK, and look what I get, and what I'm particularly here looking for is, where is it? Come on, give me the one that I want. The problem, internet is a great resource, but then sometimes it just doesn't really give you the actual bit that you want. And there is a very particular one that I'm after, and I can't find it. Isn't that hilarious? There we are. So we've got strong acids from 1 to 3. We've got weak acids from 4 to 5. Neutral being 7. Weakly alkali from 8 to 10. By the way, it shouldn't be that. It should be to 11. That's ammonia. By the way, ammonia is 11 and it's a weak alkali. And strong alkali should be from 12 to 14. The internet is a great resource, but often commonly has faults. So they've asked you there for a pH of a weak acid. And so immediately you go, oh, 1 to 3 is a strong acid, but 4 to 6 is a weak acid. And which one's right in the middle of that range is 5. So nice and easy. We've got there, of course, is a strong acid, because, of course, the pH scale actually starts at 0. Oh, 5 is a weak acid. 8 is a weak alkali. And 14 is a strong alkali. Go on to the next one. Effervescence occurs when an aqueous solution of ethanoic acid is added to the solid sodium carbonate. Which gas is effervescent? So guys, it's the carbon that, of course, I've taught you year 11s, that if you ever have a carbonate, you are always going to get carbon dioxide. If you'd like to see the equation for that, now, year 11, they can do it. So we've got sodium carbonate. First mistake some students make is giving the incorrect formula, the 2, of course, being the trick. I'm going to add that. Let's use the structural formula of ethanoic acid. Now, I'm just going to highlight the bit that makes it acidic. That H is what makes that an acid. And what's going to happen is that this is going to dissociate and react. We know that acids give off H+. I'm going to form carbon dioxide. I'm going to form water, and I'm also going to form sodium ethanoate, which is my salt. So that equation is a lovely equation. Then, of course, I need to balance it. 2 sodiums, 2 ethanoates. I'm going to need 2 ethanoic acids, and I think that now all adds up. So nice equation, definitely worth having a look at, because they could potentially give it to you. They could, of course, run you through the normal. How do you test for carbon dioxide? Bubble it through lime water, turns cloudy, white precipitate. How do you test for water? You test for water with anhydrous copper sulfate, white to blue. Ethanoic acid reacts with ethanol. Right, this is part of the brand new spec of the Edexcel iGCSE. Ethanol to form an ester. Give the name of this ester. Right, let's break this particular question down. So I've been given I'm going to make my pen a little bit fatter for this particular situation. So I've got ethanoic. Let's have a look at what ethanoic acid looks like. So there is ethanoic acid in its full glory. And then let's have a look at what ethanol looks like. Now, this is actually specifically mentioned on your specification. This ethanol and ethanoic acid. Right, now these two, in the presence of a strong catalyst, a few drops of concentrated sulfuric acid, these will link together. And you can see I'm going to lose, there's H, there's H2, and then take away the O. I'll take away that one. So these guys are going to break off and form water, H2O, and I'm going to link together to form our ester. And our ester, it's nice to just reinforce something I may have taught you guys for the first time in this webinar, which is kook. If you have a kook, then you have an ester. Let's turn that picture. There's our displayed. Let's turn it into the structural. CH3. Let's actually highlight this. CH3, CH3. COO. Oh, look, there's my COO. And then I join directly onto another C. So there's my kook. And CH2, which is here. And ending with my CH3 on the end. So really nice just to kind of walk you through in color code the turning of a displayed into structural. It's quite a useful process, but it is also really useful to recognize kook. You see kook, then you have an ester. Nice, easy way of doing it. Okay, so it then asks you to name it. So how do you now name this? Well, we started off with ethanol. This is ethanol. And I've also got ethanoic acid. So when this forms an ester, I form ethyl ethanoate. Now, what I'm trying to do here is trying to link the names together. And this one is ethano. Now, it started ethanoic. So my ethanoate, this section here is him. And the alcohol now becomes a branch attachment. So becomes ethyl. So now, I don't know what other esters they could ask you for now, but being esters being new, highly likely to make an appearance. Anybody who's been going through recent exams of subjects that I've also traveled over, you're recognizing that they're asking a lot of questions on the new particular topics, physics being one of them that did this. So if I use methanoic acid, and I add methanol, then I go, I'm going to form, this is methanol, the alcohol becomes a branch of methyl, meaning branch, and the methanoate is my ending, methanoate. So the oic becomes an oate. So nice to see how the names put together. Again, very much expecting to see it. It then says, draw the displayed formula of the functional group in an ester. Now we've got a few families at GCSE. You've got 5, and the kook middle is what's called the functional group. Now a functional group is the part of a molecule that gives it its chemical properties. So Ekim's asked a question: if they ask for one repeat unit of a polymer, can you square bracket it and add an N? Of course you can. Of course you can. If you're drawing any polymer, you should always add a square bracket and an N. Just to let you know, by the way, that that's actually gone at A level, which is irritating. They should really make a choice there. But yes, square brackets and an N, absolutely. Add it in. Thanks, Lucas. It's Kayun. I always get confused with the name being different. I do apologize. Kayun, sorry. I'll come back to that, Kayun. I'll come back to it because it was a great question of yours. And I'll come back to that when we hit to polymers. Okay, so of course here, guys, they're getting you to do the whole lot. They've given you molecular, they've gone to structural, they've given you displayed. Well, the great thing is it's giving you loads of support all the way through, and usually most people will be able to translate that in. Even for one repeat unit? Yeah, of course you would. Well, why wouldn't you? I mean, at GCSE, you can add this, if you're drawing a polymer, because it's a repeat unit, and the square brackets are saying this unit, and the N meaning any number of repeating units. To be fair, I don't actually think Edexcel will care if you put in the square brackets and the N at all, but I would always put it in at GCSE. I'm tempted to do it. I'll come back to that. Okay, ethanol is manufactured in, right, this is my other big prediction, folks. You, of course, you now have only 4 industrial processes. Only 4. They have removed 4 others, which means they've got to ask them, and they ask none of them on paper 1. What this means is they must be on paper 2, and I'm expecting ethanol to appear on a very heavy scale. Make sure you have revised the production of ethanol by fermentation and direct hydration of ethene, and that you can give the pros and cons for each process. I'm expecting it to be there. So, to turn ethanol, they take ethene with steam in the presence of a catalyst. Give the name of the catalyst used. Concentrated phosphoric acid. State the temperature and pressure used for this process. The temperature is 300 and the pressure is 60 atmospheres. Nice and easy. Now, just to quickly mention, students often go, has the Haber process gone? And the answer is it has. However, they are expecting you to be able to get given conditions and be able to understand why those conditions are chosen. So I'll talk about that a little bit later. But those conditions, guys, you've got to know. Next, copper. So we're into a good old bit of bonding. Copper is a metal. Graphite is a form of carbon, which is a non-metal. Both copper and graphite have high melting points and can conduct electricity. The diagram shows the arrangement of atoms in copper and in graphite. Describe in terms of electrostatic attractions the bonds between the atoms in copper and the bonding between the atoms in graphite. So, of course, we know in copper it is a giant lattice of cations surrounded by a sea of delocalized electrons, and there is the electrostatic attraction between the sea of electrons and the lattice of cations. Next, graphite. It is a giant covalent structure. The bonds are covalent bonds within the layers, but weak intermolecular forces between the layers. There is also, you need to explain the bonding between the atoms. Oh, I think that's it. Covalent bonds between the atoms, the electrostatic attraction between a shared pair of electrons and the nuclei of each atom. Between the atoms and graphite. Oh, I'd want to go between the atoms. That's very true, actually. The bonds between the atoms are covalent. So, I mean, I did it completely on the exam paper, but I would definitely not be wanting to run Susan Boyle there, since it's only going to be 1 mark for each one. They're wanting you to just simply talk about the bonding between the atoms. Electrostatic attraction between the cations and the delocalized electrons. Covalent bonds between the atoms. The electrostatic attraction between the shared pair of electrons and the nuclei of each atom. That's a really tricky question because lots of people will overthink that. Explain how copper conducts electricity. Copper has a sea of delocalized electrons. These can flow through the structure, carrying the charge. Not complicated. For covalent, isn't it a strong electrostatic attraction between the nuclei and the shared pair of electrons? Lucas, yes, it is. That's exactly right. By the way, you need to be careful because you can't just say between nuclei. You have to say that between nuclei, the nuclei of the 2 atoms and the shared pair. Just Lucas, just to let you know, by the way, that for the covalent, I'd often do this: nuclei, nuke of the 2 atoms, and it's the electrostatic attraction between the 2 nuclei and the shared pair of electrons. That picture will get you pretty much all the marks. Oh, as long as you label it. Electstat attract, and we've got shared pair of electrons. Shared pair of electrons. Nuclei, you get all the marks for that one. That's good. Okay, next. Explain why graphite has a high melting point. Right, you're running Susan Boyle, folks. Structure, bonds, strength, number, energy. So, structure is a giant. Graphite is a giant covalent lattice. However, you had graphite on the first paper, which means I'm not expecting it to reappear again. So we're expecting metals to appear. I'm also thinking polymers are going to make an appearance as well. Bonds in the layers are covalent. Between the layers are weak intermolecular forces. Covalent bonds are very strong. All bonds must be broken. There are millions of them. Lots of energy are needed. Notice, that's really evil. Look, guys, 2 marks. I have no idea which 2 they want. I've got to give the lot, and I'm not even going to consider it. I'm going to explain it properly and give good chemistry. Always. Next. Okay, a usual empirical formulae. I don't know whether or not you had an empirical on your paper 1. If you didn't, it's very likely to make an appearance, so please practice them. So it's given you the percentages of each element. They've even listed it for you, and they've even given you the relative atomic masses. What's the point of giving you a periodic table? Anyway, fine. So take the percentages, turn them into grams. There you go, grams, and then we know grams over rams because we need to count particles. Moles counts particles. Divide them by 56, the AR of iron, divided by 52, the AR of chromium, and 16 of oxygen. You get those. Those are the moles. Now we want to actually find out what the whole number ratio is. Divide them all by the smallest, and you get a whole number ratio. And there's our formula, which matches. There's always nice. Next. Okay, the stages involved in the extraction of chromium from chromite. Chromium is reacted with potassium hydroxide and oxygen to form potassium dichromate. Potassium dichromate is heated with carbon to form chromium oxide, potassium carbonate, and carbon monoxide. The chromium oxide is heated with aluminium. Complete and balance the equation. Right, so guys, I'm actually going to run this in its entirety. Okay, because this is the hardest GCSE balance I've seen in a while, so definitely worthwhile doing it step by step. So, 1 iron, 1 iron. Next, just move on to the next person. 2 chromiums, 2 chromiums. Wow, doing well so far. Next, oxygens. Right. 4, 5, 6, 7. I have 7 oxygens there, folks. Let's just quickly make a note of that. 7 oxygens. How many on this side? 1, 8, 9. Oh, that's awkward. Hang on a minute. How do I get this? This side has 9. Right. Who can I change that'll change nobody else? Well, guys, I've got pure oxygen there. So all I have to do is add a bit more oxygen to balance out to that 9. Well, at the moment, it's 7. What I need to do is add more to this. If I put a 2 there, right, how many oxygens do I now have? I now have 4, 5, plus another 4. That's 9. Now, oxygen's now balance. I like it. Oxygen's done. I've changed somebody. I'm going to start my process all over again. So I've got 1 iron, 1 iron. 2 chromiums, 2 chromiums. 4, 5, plus 4. I've got 9 there. 1, 8, 9 there. Next, potassiums. How many potassiums do I have here? I've got 1 on that side. 1 there. I've got 2 here. I need to double it. Right, double that. I have changed somebody. Right, 1 iron, 1 iron. 2 chromiums, 2 chromiums. Oxygens, 4, 5, 6. I've now got 10 oxygens. And on this side, I have 1, 8, 9. Right, how do I... Oh, I can reduce this one by 1. So what I can now do is, instead of having a whole number, I can actually use... I need to get rid of 1 atom. I had a 2 there, which means I had 4. But the problem is that takes me to 1 over. I want 3. How do I get 3 out of that 2? I'm going to put in 1.5. Right, that now takes me back down to 9. My oxygen's now balanced again. Let's check everything. 1 iron, 1 iron. 2 chromiums, 2 chromiums. Oxygens, 4, 5, 6, 7, 8, 9. 1.5 times 2. Oxygens, 9. Right, next one, potassiums, 2. Hydrogens, 2. Hydrogens, I'm done. So now for those students who don't like the fractions, and you shouldn't really leave them in at GCSE, what I should now do is double everybody to get rid of that half. So 2, 4, 3, 2, 2, and 2. And I can check that if I want to. So I've got 2 ions. I've got 2 ions. I've got 2 ions. I've got 4 chromiums. I've got 4 chromiums. Oxygens, I've got 8. 8 plus 4 is 12. 12 plus 6 is 18 oxygens. I've got 2. I've got 14. That's 16. 16 plus 18. I'm good. Potassiums, 4. Hydrogens, 4. It all adds up. Guys, that's the hardest GCSE balance I have seen in a long time. For those students, oh, hey Elijah, thanks for coming. It's nice to see you. So guys, that is the hardest I have ever seen them do. And they do take a bit of practice. It gets easier, I promise. So if you want to come and get some practice questions off me, I will happily give you some. I've got dozens and dozens of them. Okay, the next thing, write a chemical equation for stage 2. Stage 2 says potassium dichromate is heated with carbon. Oh, potassium dichromate is heated with carbon. They've given you potassium dichromate, which is there. You know the symbol for carbon is just C. And what you're going to make? You're then going to make chromium oxide. They give you its formula, and potassium carbonate and carbon monoxide. I've copied them over, and then I've balanced it with my 2 carbons. Again, hard equations. Explain which element is reduced in stage 3. Okay, stage 3 is which one's being reduced, and the answer is chromium. And the reason being, folks, is that you have to work out some charges. The charge on chromium here, by the way, you don't actually have to work it out, they tell you. it's chromium 3+. I'm going to make my pen thinner at this point. So that there is chromium +3, and it's ending at chromium 0. So what that means is it's going from +3, and it's being reduced in charge to 0. So the chromium element, it actually asks which element is being reduced, and the answer is chromium is reduced as it has lost oxygen, is what I've said there. It's absolutely correct. It has lost oxygen going to chromium. I'm allowed to say that, but I can also say because it has gained electrons if I wish, but losing the oxygen is easier. Next, explain what the reaction in stage 3 suggests about the reactivity of aluminium compared to the reactivity of chromium. Right, well, guys, I love what they've done here, because this reaction here is a clever spin-off of the thermite reaction that I showed you last year. Thermite is when you use iron 3 oxide and aluminium powder. And aluminium is far more reactive than iron, so it steals the oxygen, and I form iron metal, and the iron comes out liquid. Very unusual, that. It's very, very, very exothermic. Hot enough to be able to melt steel at 1600 Celsius. It's crazy hot. Balance the equation, can't not. But this is because aluminium is far higher in reactivity than iron. Now, for those students who are very diligent and who like to learn the extra things to make their chemistry lives easier, most people here will have well, some people will have learned parts of the reactivity series. Now, of course, what that means is it does make life a little bit easier, because you would automatically know that iron is below aluminium, but chromium does not make an appearance. What that means is the only way that you'd be able to tell its reactivity is by doing a reaction with another metal. And in this case, aluminium is more reactive than chromium. Nice question, that. So it says, and explain why. Aluminium is more reactive than chromium since it displaces chromium oxide from its oxide, chromium from its oxide. Next, ethanol is oxidized with using potassium dichromate. Guys, another prediction. I'm predicting them to talk about this oxidation of alcohol. This is relatively new, and there's 2 methods for doing it. Leave it open to air, or by using potassium dichromate, which changes from orange to green. Do a little bit of revision on this section. Name of compound X. So the ethanol turns into ethanoic acid. This is actually how we, this is talking about how we make vinegar. I'll add a little bit more on that later. Okay, so next question is enthalpy change. So this is heat change, enthalpy. So we are doing an internal calorimetry. We have a beaker with a polystyrene cup and a thermometer right in the center. It says use the measuring cylinder at 30, I'm going to highlight my data, 35 centimeters cubed of 1 mole per dm cubed citric acid. It's given us a concentration. Polystyrene cup, and record the initial temperature. Add 7 grams of solid sodium carbonate and stir the mixture. Record the lowest temperature achieved. Right, so initial temperature and lowest temperature reached 4.1. So first thing I did was I worked out what the decrease is. An emphasis on the word decrease, folks. That's important. Show the heat change during the reaction is about 2,500 joules. So we drop straight into Q equals mc delta T. So the mass of water, remember, everything comes when you're using Q equals mc delta T, it's about the water. Students often say, but there's no water here. But there is. This is because it's a solution. Citric acid is given a concentration. This is in water. And that's the volume here is the volume of water. The volume of the solution is the volume we're going to use. So the mass of water is 35. The heat capacity, which is given to us in the question, which is there, is 4.18. And we're going to multiply it by the temperature change. And we get 2,472 joules, which is approximately 2,500, like that. Next, calculate the enthalpy change. We see this coming, don't we, guys? The next equation, we remember that when we do enthalpy change, folks, we remember for enthalpy, by the way, which is all about heat energy changes. So enthalpy, we have a few equations we need to use. The first one is Q equals mc delta T, followed by divide by 1,000. That's to convert the joules to kilojoules, followed by delta H equals Q over N. And then we have to work out moles to be able to get that. So let's move back to the question, because I wrote down my equation, work out the enthalpy change in kilojoules per mole. Well, there's my equation, and I had, the first thing I needed to do was change my joules in the previous question into kilojoules. I've divided it by 1,000, so I have 2.472 kilojoules. Now, where did I get my moles from? My moles comes from, there we go. Right, number one, it tells you 7 grams of excess sodium carbonate. Excess. This means we ignore it. But then that means we need to use this for our moles. Second equation, number of moles is C times V over 1,000 for our solutions. So we have 1 mole per dm cubed as the concentration. That's moles per dm cubed. And then we have 35 centimeters cubed. Divide by 1,000 to convert it into dm cubed. And we get our answer. We put that number, our final answer, into here, and we get plus. You must remember, you must include your sign because it's endothermic. Plus 70.6. Next. Okay. Draw it down. By the way, it's endothermic. This is important, guys. Endo. It's got cold. Look at the temperature. Look at the data. It's screaming endo at us. Because look how cold it got. Lowest temperature reached, 4.1. That's chilly. Very chilly for Malaysia. Not so chilly for the UK. So, okay. So it then says, draw an energy level diagram. Well, just a reminder that energy level diagrams are lovely and easy. We have exothermic. And then we have endothermic. Yeah, this one's exo. It loses heat. And this one is endo. It has gained heat. Well, this has gained 70.6 kilojoules of energy. So, draw the graph. To draw my 2-axis, energy, reactants, products, and it must go up. Join them with the arrow and lob your people on the shelves. Reactants over here, products over here. Nice and easy. Next. Explain why it is better to use a burette rather than a measuring cylinder when measuring the volume of aqueous citric acid. Guys, right, as soon as I hear that, I'm going up to my my question. Use a measuring cylinder. Oh, when drawing these energy profile diagrams, things for a catalyst, do I have 1 or 2 curves? Good question, Winkit. I'll give you the third graph. I think it's a really great question you've asked there. There is a third one, isn't there? Let's do exo, but here's my original profile. What this here is my original activation energy. I've got to get my particles up to here to break their bonds. And then they come down the hill and make new bonds and give out energy. So this gives out energy, this takes in energy, and that's activation. Well, the problem is that activation energy is very high. If I want now to add a catalyst, what I would do is the second picture is I would do this. I have a catalyst shelf, and I will draw a hump up to it and a hump from it. Like that. I just need to make sure that the hump I draw is smaller than the original, and I'm done. So 2 curves. Yeah, you can, by the way, there is another one, and a simpler one for catalysts. And I prefer that one. That's a better graph there, guys. That's a better graph. And this is your catalyst shelf. And this is your activation energy for the cat. There is another one, which is you can simply do that. And that's the activation. Shouldn't make that a little bit higher. That's the activation. The answer is you can do either, but you have to recognize both. But you can draw either in your exam. Next. So, explain why it is better to use a burette rather than a measuring cylinder. A burette is more accurate since it has a smaller scale, so can measure smaller changes. You're measuring out 35 centimeters cubed. If you're on plus or minus 2 on a measuring cylinder, then you're going to be out by quite a way. So you're always wanting to use a burette if possible. It's interesting, by the way, I wouldn't actually use a burette to measure that out. If I was measuring out 10 centimeters cubed, I'd use a burette because that's a small volume and the error is going to be massive. But anyway, more accurate, It measures smaller changes due to having a better scale. Right. A student is asked, right, guys, titrations, you all know they're going to be there. It's going to be there, folks. This is going to be a 6 marker. Make sure you've learned your titration method. It is just a story. You've just got to learn it. So, describe how to do this titration. Assume all glassware is clean and do not need rinsing. Using a graduated pipette, add 25 centimeters of the acid to the conical flask. Add 3 drops of indicator. By the way, so why do we use a graduated pipette for the 25? Because it's really accurate. It gives us a really, really accurate volume. And since since a titration can be done to within a drop accuracy, then we're going to need a piece of equipment that's going to have similar accuracy, hence the graduated pipette. Next, and it also must be in a conical flask because conical flasks are shaped to allow you to swirl it without spilling. Why do you add 3 drops of indicator and not 10 drops of indicator? Because indicators are themselves acids or bases, and if you add too much indicator, then you're going to have the wrong titer. Using the burette, add the sodium hydroxide quickly at the start and then dropwise near the end point. Stop when permanent color change turns pink. Record the volumes on the burette at the start and at the end. Repeat until concordant results. Learn that method. Just learn it, folks. It is going to be there. Next. In this titration, 23.85 centimeters cubed of sodium hydroxide are needed to neutralize the sulfuric acid. Guys, this was really hard because they didn't give you the equation, did they? No equation. That was pure evil. I've never seen them do that at GCSE, ever. They have always given the equation, except on the specimen paper. Be warned. Sulfuric acid, sodium hydroxide, sodium sulfate, and water. And balance. It's in a 2-to-1. So we work out the moles of sodium hydroxide. C times V over 1,000. Concentration was 0.4 from previous. Volume was this. Divide by 1,000. There's my moles. Oh, have I gone? Oh, yeah. So it says in here, work out the moles of sodium hydroxide. Done. Nice and easy. Oh, they're giving you the equation. Oh, and there's the equation. Next, calculate the concentration of the sulfuric acid. We've just worked out the moles of him. There they are. It's in a 2-to-1 ratio. Divide by 2. Gives me the moles of sulfuric acid. Right, reorganize C times V over 1,000. So number of moles times 1,000 over V gives me C. Input your numbers, and there's your concentration. We know they're going to be there, folks. Next, a solution of sodium sulfate is formed by the neutralization of some diluted sulfuric acid with sodium hydroxide. Describe using the method of crystallization how you obtain a pure, dry sample of sodium sulfate. Right, salt preparations, learn them, folks. Another set of stories to learn. Take the solution and heat it. Evaporate. So mix, oh, by the way, you've already been given the solution. Take the solution and heat it. Evaporate 80% of the water. Use a glass rod, touch it to see if crystals form. Leave to cool down, filter out crystals. Leave to dry in a drying oven. Check melting point for purity. If they ask you to check the purity, then you're always doing a melting point. If you're doing it with a liquid, it's its boiling point. Next. And guys, that brings us to the end of the paper. Relatively short, but definitely challenging. Now, what you'll notice in this, right, so now here's what I'm now going to do. I'm going to give you 20 more minutes just having a look at the amount of stuff that they've got to ask in this paper. All of this, I have gone through your entire specification and chopped out all of the higher level stuff. So, predictions for your paper. So by the way, you are more than welcome, Year 11, to come in and see me in school anytime you like to discuss what I'm about to talk you through now, because I'm not going to spend hours on the internet doing this. I'm just going to quickly do some predictions. So, number 1, I predict that you are going to see a solubility curve question. That, I think, is going to be there. Next, Understand how you calculate volumes of concentration in solutions. We know C times V over 1,000 is going to be there. In the specimen paper, there wasn't a single gas question. I'm expecting it to be there. Number of moles is V over 24. Next, metallic bonding. It was on your paper in the paper 1, so I'm not expecting it to be there, but they may talk about electrical conductivity, but I doubt it because I think you already had one. Electrolysis is going to be there. Please note that they've given you specific examples there. I'm happy to discuss them further in school, but they're definitely going to ask you some electrolysis questions, and they're focusing specifically in your specification, lead 2 bromide, solutions of sodium chloride, dilute sulfuric acid, and copper sulfate. I am predicting sodium chloride. They're going to give you the electrolysis of brine, and you're expected to know your products. So you need to know that you're going to make, I won't get into that. It's on the electrolysis webinar. Right ionic equations for the reactions, it's going to be there. Next, trends in reactivity of group 1. Well, it could be there. I didn't see that on your paper 1, but it could be, but I don't think so. I think they're going to give you, explain the trends in group 7 and all of your, could we please go through equilibrium shifting with temperature and pressure? Yes, we can. I'm expecting what are the products of the electrolysis of sulfuric acid? Hydrogen and oxygen, funnily enough. So, okay, Yo's asked a really good question. If you electrolyze sulfuric acid, in the beaker, you have 2 ions. The acid goes in and it splits in 2. I have 2 H pluses and SO4 2 minus. Now, lots of people think that you're then going to form some kind of sulfur product, but you don't. The reason being is this is aqueous, which means we have an additional ion. We've got SO4 2 minus and OH minus from the dissociation of water. For those people who want to see that a little bit more clearly, I'll draw that larger. So we have sulfuric acid drops in, and it gives us H+, and SO4 2 minus. No more sulfuric acid. It's gone. It's dissociated. But also, we know that water also ionizes to give me that and that. But there is lots of water as well left over. So here's the thing. You're always going to get hydrogen gas. And it's going to appear at the cathode, because the cathode attracts cations. So the hydrogens are going to go to the negative electrode and form hydrogen gas at that. 2 H pluses gain 2 electrons. They go through. Reduction is the gain of electrons. Hey, Ansh, good to see you. And I'm going to form H2. Now, at the other electrode, this is trickier. At the other electrode, it is positive, and I have 2 potential ions, sulfate and OH minus. Which one is more stable? The sulfate ion is more stable, so it won't do it. So what's going to happen is the OH minus ions are going to form oxygen gas. Now, when they do this, you're also going to get, you've got to balance this half equation. Now, you'll never expect it to build this, but you're never expected to actually write this out yourselves, folks. Balance, so I'm going to add H2O over here. Then I'm going to add H plus over here. And then my electrons, and now I need to balance it. So I've got 2 oxygens there, 2 oxygens there, 3 H's here, 3 H's here. Charge on this side is +3. Charge on this side is -1. Bring somebody down, add 4 electrons. So that's actually what's happening, Yo, just so you know. So you make hydrogen and oxygen when you electrolyze sulfuric acid. So it's nice to see why the spec points are important to go through. I'm very much expecting those to appear. Or obviously, if they decide to go for copper, it's going to be electroplating. Also, if an exam question asked, in the electrolysis of brine, sodium hydroxide, hydrogen and chlorine gas are formed, why isn't sodium metal formed? What would be the answer? The reason being is that sodium, right, so here's your answer in a picture. At that electrode, you've got two ions, which can go and collect electrons. But hydrogen is lower in reactivity. What that means is it can gain it more easily. So your answer, yo, is hydrogen, H, I'm going to put hydrogen, I will properly do it. Hydrogen lower in reactivity compared to sodium, therefore H plus gains electrons, forming hydrogen, not sodium metal. So it's all to do with reactivity. Next, more predictions. Right, extraction of metals. So guys, extraction of metals has been cut and cut and cut and cut over the years. So there isn't really much else to really talk about, but just to mention, ores. I've got a feeling that they're going to actually ask you for the definition of an ore, which is a rock that contains sufficient metal or metal compounds to make it worthwhile extracting. Learn it. So I'm expecting a definition to appear there. Next, explain how the method of extraction of metal is related to its position in reactivity, electrolysis, and carbon. Anybody above aluminium is electrolysis, below carbon is going to be blast furnace. Be able to comment on the metal extraction process given information. Right, they took away the blast furnace in terms of what you're needed to know, but they can still give it to you and expect you to be able to understand it. So since that change has been made, I'm expecting them to give you a really bizarre process, very similar to the one they gave you in your specimen. They're flagging this, folks. They're going, check out this crazy extraction of chromium. And they're just asking you to be able to use your chemistry understanding to be able to do stuff, balancing an equation and writing an equation you've never seen before. I'm expecting that to appear again. They could ask anything from tungsten through to titanium. I've taught you both. I'm expecting it to be there. Explain the use of aluminium, iron, steels. I'm expecting high and low carbon steel was not in the specification. Have a read about it. If you're unsure, come and see me. Explain why alloys are harder than pure metals. The atoms are of different sizes in alloys, therefore the layers are disrupted. They can't slide as easily. Describe how to carry out a titration. It's going to be there. It's going to be worth 5 marks. Learn it. Describe an experiment to prepare a pure and dry salt. Guys, they're going to give you one of these, but I don't know which. You need to just learn all 3 and make sure you've checked it. Right, we know that they're going to give you a mexobendo. Now, in your specimen paper, there were no bond energy questions using burp. I've got a feeling that burp is going to appear. Reactants minus products using your bond data. Going to appear. Next, right, equilibrium. It's been cut and cut and cut and cut. I think they're going to give you an equilibrium, and they're going to give you probably one you've seen before, which will probably be Haber. Or ethene with steam, and ask you to discuss the conditions. Okay, next thing, guys, alcohols. There's going to be a 5-mark question on the pros and cons of making ethanol. So they're going to ask you to talk about fermentation being low energy, renewable, high labor, and being able to look at the pros and cons of each one and compare them. They're going to give it to you, folks. Come and see me if you want some support with it. Carboxylic acids, I don't think they're going to give you much on it. I think they're much more likely to give you esters. I've got a feeling that they're going to give you a nice basic ester question, probably one you've never seen before, and they could very well give you a polymer question, but because they didn't have any polymer questions at all. So I think a polyester will probably appear, but it's very, very straightforward. Again, come and see me if you need the support. Now, I did have somebody, I had Kayun ask me, can we please go through equilibrium shifting with temperature and pressure? This will be my last bit for this webinar. So guys, I've made my predictions. They're there. So certain bits I've just said, no, but that's what I think is going to be on your paper. All of those yellow arrows. Make sure you're focusing on those questions and that bit for revision. Okay, just to now go through a little bit of equilibrium since Kayun has asked it. So equilibrium, I'm going to make my pen a bit fatter for this. So equilibrium. So they are very likely to give you an equilibrium you've used because you have two to think about. You have got ethene with steam in equilibrium. Steam, probably there, to form ethanol. There's one equilibrium you have to know. And then you also have to know, he was gone, technically. What's the other equilibrium that you've got to look at? Technically, esterification is an equilibrium. Oh, there was another one that was in my head. It's gone. Anyway, not that it matters. So let's just look at this particular example in making ethanol. So we want to know, now just to let you know that there is minus 43 kilojoules per mole over there. We get given little bits of data. So for the polyester drawing thing, can you change the CH2 part into like sticks? Yes, you can. Absolutely. I don't mind. You can do a full picture if you like, Kayan. Okay, so we know that when we get equilibrium questions, we're going to get raise temperature, raise temp, what effect on yield. So this is about how much ethanol we get out. This is the yield idea. So what we're going to say is we have raised the temperature and we're going to run COFS. Now, COFS is just my method of teaching this and giving you a process. And the K stands for knowledge, O stands for oppose, F stands for favors, and S stands for shift. So what's the knowledge here? Well, if you raise the temperature, the bit of knowledge is about the exo-endo. Decrease as equilibrium shifts because the forward reaction is exothermic. Correct, spot on. Yeah, lower yield of product. Absolutely right. Just to, in terms of Lucas, just to make sure you hit those marks though, because it can be 4 marks. You got in your answer there, you got the knowledge. The forward reaction is exothermic. So the knowledge there is that this way is exo because that is negative and this way therefore is endo. So knowledge, forward reaction is exothermic. Exothermic. Next, oppose. Now this, you must be very clear in. It's the most lost mark at A level, in fact, for equilibrium, which is we raised temperature, raised temp, therefore equilibrium will reduce temp. You've got to say this. That's 1 mark. You've got to say what the opposition will be. Then what's it going to favor? So Lucas, you missed both of these in between points. But I love the fact that you know what the answer is, which is great. So how is the equilibrium going to lower the temperature? It's going to favor endo reaction. We know endo gets cold. Favor the endothermic reaction. Let's have a quick look which one that is, which is there. And so we're going to shift it this way. So shift from right to left, shift right to left, shift right to left, lower yield. Kayan, does that help? Does that all make sense for temp? Question number 2, pressure. Mr. Duncan, can you check your emails as soon as you can? Okay, I'll have a look, Andrew. Okay, so next one, let's choose a different equilibrium. Let's go for something that you might not have seen. I'm dragging up equilibriums out my head now. I don't want to start making them up. I'll just stick with this one. SO2 plus O2 goes to SO3. This is called the contact process. I'm going to balance it. Cool, so there's my balanced equation. Let's now talk about pressure. Question. Let's lower pressure. Lower pressure. What's the effect on the yield? Yield? Is it going to increase or decrease? So, answer, coughs. So what's the knowledge in this case? The knowledge about pressure is the particles on each side. So I have got 3 particles over here, 1, 2, and a third with oxygen, 2 and a 1. I've got 3 particles on that side, but on this side, I only have 2. There's my knowledge. I've got 3 particles on left, 2 particles on right. Okay, oppose. If I lower pressure, equilibrium will raise pressure. How do you raise pressure? How could you favor this? If you want to increase pressure, you need to make more gas. So I've got 3 particles over here and 2 on here. We want to go this way. Favor side with more gas, with more particles. Shift. I'm going to shift from right, left. No, hang on. From right to left. Shift right to left. Yield decrease. Does that help, Kayan? I hope that helps. I'm going to end my webinar there, folks. Can I say I'll bring you guys back to me now at this point. Let's see if I can bring it back to here. So let's do sharing screen, stop. Year 11, thanks for stopping by. I really appreciate your time. I hope you guys, and I wish you guys all the best of luck. You're going to do great. Come and see me anytime in school. If you want to discuss my predictions a little bit further and go through some example questions, I'm more than willing to do so. But I wish you all the best, and I hope all your exams have gone okay so far. And all the best. Take care, guys. Have a nice rest of your evening. Bye.